In the previous video lesson on the motion of satellites, I suggested that a satellite experiences an acceleration that we refer to as a centripetal acceleration, and that centripetal acceleration can be calculated if you take the tangential speed of that satellite squared divided by the radius of its orbit. So this is a general equation for the acceleration involved when an object moves around a circular path at a constant speed. We refer to this as uniform circular motion. Well, we refer to this equation as the equation for centripetal acceleration. And this centripetal acceleration is associated with uniform circular motion. So it doesn't have to be necessarily a satellite orbiting around a planet. This can be any situation where an object moves at constant speed in a circular path with a radius of r. So here's an example of maybe a race car driving around a circular track. So pretty clear what we mean by r, right? It's nothing more than the radius of the path. And then the reason we put this subscript t next to v is it represents what we know as the tangential velocity. In other words, if you think about the law of inertia, a car that's attempting to drive in this direction on a racetrack, if it encounters a patch of ice or an oil slick, then there's no force of friction that can push the car toward the center of the circular path, and the law of inertia takes over, and the object would want to continue sliding straight ahead according to the law of inertia. So we don't just call it speed, we refer to this as velocity. And that's a concept that we went over in a previous lesson on the difference between speed and velocity and the difference between scalars and vectors, right? So speed is strictly the number of meters per second, and it's a scalar quantity. Velocity includes the number of meters per second plus information about the direction of travel. So we refer to velocity as a vector quantity. So we're dealing with vectors in this case. So the radius is a vector and the velocity is a vector quantity. Okay, so that's it. The t here represents tangential as a way of describing a direction for the speed. We could likewise talk about a ball that's whirled around on the end of a string, although I'm not real excited about the drawing in this case because it looks unrealistic. I don't think that the string could make this sort of an angle. I don't even think that you could whirl the ball on the end of a string and have it remain in a horizontal plane. Let me do a little editing here. See if I can scribble over this. Okay. Bear with me. Okay, I like that better. So yeah, let's imagine this case. The ball moves around. Oh, that's a little too thick. Oh, okay. Yeah, what if the ball could be spun in a circle like this? Then the tension in the string would be pulling the ball at all times toward the center. So we could refer to that tension as a, not centrifugal, but once again, a center-seeking, a centripetal kind of a force. However, I don't see what could possibly be offsetting the pull of gravity. So I know that the tension would pull inward, gravity would pull downward, but there's nothing left to pull upward. So truth is, that the string would always have to make a little bit of a downward angle. So let's try all this editing again. We'll get this right. The string certainly can't angle upward. And it can't even maintain a flat 0-degree angle, but it's certainly possible to whirl a string and have the string dip like this a little bit. There we go. That's more realistic. And the ball can move around. Now the path of the ball is in a horizontal plane, but the string is not directed horizontally. And in that regard, there are two components to the tension in the string. So I'll highlight this in red to represent the tension that's pulling a little bit inward and a little bit upward on the ball. And just like we did with velocity vectors in our study of projectile motion, we can break that tension vector into two components. So it pulls a little bit inward and it pulls a little bit upward. So if we wanted, we could call this T and put a subscript X to say that's the horizontal component to the tension, and a T with a subscript Y for the vertical component. So it's this horizontal component of the tension that's directed straight toward the center of the circle, and we would refer to that then as the center-seeking or centripetal force. Now, the vertical component is just there to perfectly cancel out the pull of gravity. So the net result along the y-axis is that there's no force at all. So the object doesn't want to accelerate up or down. In the up, down, or y direction, the net force equals 0, so the acceleration along that axis is 0. But there's definitely going to be an acceleration along the x-axis, and that acceleration should be equal to v squared over r, where r is indeed the radius of the circular path, and v is actually v tangential, the speed with which the ball directed tangentially to the circular path is equal to. So, by the way, let's look at the units involved in an equation like this. It says we're supposed to take some units of meters per second and square that, and then divide that by units of meters. So we get meters squared per second squared per meter, which would leave us with meters per second squared. So at least dimensionally, this equation that's suggested for centripetal acceleration seems to be correct. Let's get into it with a little more detail. So whether this is the overhead view of a car going around the racetrack or the overhead view of that ball that's whirled around in a circular path, or any situation where an object is moving with constant speed on a circular path, we can place the object maybe initially right here so that the initial tangential velocity vector points straight up. Move that a little bit. Okay, and then let's say the object moves to this final position. To where the tangential velocity now points in this direction. So the object's now, let's say, here. Okay, then how can we show, just from a diagram like this, that the centripetal acceleration really is given by this expression a centripetal equals v tangential squared over radius? So we're going to do a little bit of vector math. And vector mathematics is different than typical scalar mathematics in the sense that, well, as a side note here, if I say what's 3 plus 4 in scalar mathematics, every time that's equal to 7. But let's think about these two vectors. What if I take a vector that's 3 units long pointing to the right, and I add to that a vector that's 4 units long pointing back to the left? The end result might be a distance of 7, but the displacement that results in a case like this is actually only 1 unit pointing to the left. So sometimes 3 plus 4 equals -1. Interesting. Or you could have another case where 3 plus 4, I didn't draw that to the correct scale. Let's try again. 3 plus, there, that's better. If we draw a vector that's 4 units, it should appear longer than the one that's 3 units. In any case, The result here is going to form a right triangle. So this would be an example where 3 plus 4 equals 5. Okay, so clearly vector mathematics is not the same as scalar mathematics. So how does this apply to the case of an object that's moving in a circular path? Okay, we'll call this V initial, and we'll call this V final. Now keep in mind, the only reason these vectors are different is because they point in a different direction. However, in each case, the length of those vectors is the same. So we're talking about something that maintains the same speed, it maintains the same magnitude, but the two vectors have different direction. So those are the two properties that define a vector quantity. The magnitude is how long you draw the vector, so there's a vector of low magnitude and there's a vector of greater magnitude. However, those two vectors share a common direction. Okay, so no explanation needed there, right? Okay, so in general, an equation for acceleration, let's say acceleration is final velocity minus initial velocity divided by time. So if all we did was subtract the magnitude of the final velocity, or I'm sorry, the magnitude of the initial velocity from the magnitude of the final velocity, you would think the numerator then would be 0. And then you might assume that the acceleration in this case is equal to 0. But it turns out that acceleration is also a vector quantity, just as the tangential velocity is a vector quantity. And in coming up with a result of 0, we're treating this like a scalar and not like a vector. So let me draw a diagram that'll help you appreciate the vector nature of velocity a little bit better in this calculation. Let's think of it like this. Acceleration is the final velocity vector minus the initial velocity vector divided by time. Okay, that's our starting point. And then we want to end up with this expression as our final result. So, how about in the second step, I say acceleration is equal to the final velocity plus the negative of the initial velocity. It turns out there actually is no rule for vector subtraction. There's only a rule for vector addition. However, you can probably guess what's implied by stating the negative of a velocity vector. In fact, the negative of this vector right here is nothing more than this vector. That makes sense, right? It's a vector of the same length, but pointing in exactly the opposite direction, and therefore is the negative of that vector. So let's graphically represent what this expression might look like in a vector diagram. So let's start by drawing the final velocity vector. We can actually just take this one and pluck it away from here. Okay, there's our final velocity. And then we're being told to add to that the negative of the initial velocity. I think I can speed this up if I make my eraser a little bigger, huh? Okay, so there we go. There's final velocity, and let's add to that the negative of the initial velocity. So here's the negative of the initial velocity, and by adding it, what we're really saying is just touch the vectors together so the tail of one vector is attached to the tip of the other vector. Let me use my eraser again and clean this up. Let's label these a little better. So there's the final velocity, and here is, careful, the negative of the initial velocity. So they're not really presented properly on the page to represent addition. I have to slide them and rearrange them so they're connected tip to tail like this, okay? So then the result, well, that covered it up a little bit, but you get the idea. I can draw this in. That's a little better. The result is the vector that goes from the tail of the first vector to the tip of the second vector. Now I want you to notice something. If we were to take that vector and move it back into our diagram, somewhere in the middle of where this change is taking place, then we would find that it points which way, right? So this represents the change in the velocity between the final and the initial value. And so the change in velocity, the delta v itself is a vector, but it happens to be pointing directly toward the center. So the change in velocity itself is tangential. So to give a reminder of the whole situation, we were talking about a final velocity vector out of that length pointing in this direction because the object ended up here starting at point A and ending up at point B. Of course, the radius remained constant during that process. So that's it. We can't just subtract the magnitudes of the two velocities, because if so, we would assume that the result is a zero. But if we're actually subtracting using vector mathematics, we find the result is not zero. It itself is a vector quantity pointing toward the center of the circle. Okay. So that still doesn't really give us a mathematical result, what we can place in this numerator. So I want you to picture some similar triangles. So what we have, if I copy this one more time, we had a final velocity vector pointing roughly like this, the negative of the initial velocity vector pointing like that, final velocity, negative of the initial velocity, and then the change pointed this way. And so there's some angle theta in this diagram. There's our delta v. Now at the same time, we have this triangle. So the distance covered by the object moving around the circle is measured along this arc length. However, the displacement just goes from point A straight to point B. So the displacement would be along this straight line path. So we could call that, well, I can't call it delta x because it's not displacing strictly along the x-axis, and I can't call it delta y. So in this case, we might call it something like delta s. Often s is used for displacement. Okay, so here's this other triangle. That's the radius. That's the same radius. And then there's this displacement, delta s. Can you convince yourself that these two triangles are similar? One way to think about it is, what if we imagined the same case, but instead of allowing this much time to elapse so that the object moves this far around the path from A to B, what if we consider just a smaller amount of time? So the object moves from point A to a smaller point B. So there's A, B. So all that happened here is we have a radius vector, the same radius vector, and therefore a smaller delta s. But in the same regard, look at this. The final velocity would point this way, the initial velocity would point this way, meaning the negative of the initial velocity would point this way. So now we get a vector diagram for the velocities that looks more like this. And so just as the angle got smaller from case number 1 to case number 2 regarding the diagram with the ratio of delta s to r, then case number 1 for the velocity and change in velocity also shows the angle got proportionally smaller. And so the difference between v and delta v follows the same ratio. Here's what I'm trying to suggest, that the ratio of delta S over R is the same as the ratio of delta V over V. Now, you might be asking, wait a minute, what V is that? Is that V initial or is that V final? If I don't include the vector notation on it, it doesn't make a difference. Because keep in mind, this is motion with a constant speed. So the magnitude of the vector is the same in either case. So, all right. And let's be clear. I'm not trying to convince you that delta S is equal to delta V or that R is equal to V. I'm saying in total, the ratio of delta S over R is the same as, that's sort of like saying the ratio of 4 over 8 is the same as the ratio of 1 over 2. That doesn't say that 4 equals 1 and 8 equals 2, but the ratios certainly are the same. So if you're convinced of that, then what if we multiplied both sides of the equation by V, which represents the constant speed for the object that's going in a circle? Well, then it cancels here, and we get delta V is equal to delta S over R times V. Okay, so we can use that to make a substitution. So I'm going to restate number 1 and 2. So remember what we're out to prove. When something goes in a circular path, it has a centripetal acceleration equal to the tangential speed squared divided by the radius of the circular path. So to derive that, in step 1, we just stated that, in general, acceleration is found by taking a change in velocity divided by time. And we found that when we let the change in velocity be final velocity minus initial velocity treated as vectors, now we can make this substitution for delta V, and we get A equals delta S over R times V, and then all this, of course, divided by T. So this is a bit of a complex fraction. We can rearrange terms a little bit and clean it up. So now we have A equals, how about I write it like this? Delta S over T multiplied by V over R. Mathematically, that's the same thing, right? So wait a minute, what is delta S over T? So if we continue this process of shrinking the angle to smaller and smaller values, we can approach an instantaneous velocity. So in fact, let's imagine the object that goes around in a circle proceeding from this point and advancing ever so slightly to this point. Okay, then this delta S over T would be nothing more than the instantaneous velocity. Right, so in step 4, now we have the acceleration is equal to V times V over R, which of course is V squared over R. So it seems like we've set out what we meant to prove. Not only do we have a way of calculating the magnitude of the centripetal acceleration, but along the way we found that that acceleration is indeed centripetal by noting that it points in a direction toward the center. So there you have it. A bit long-winded, but there's a derivation of the equation that says whenever an object moves with uniform circular motion, it has a centripetal acceleration equal to V tangential squared divided by R. So these terms, centripetal and tangential, refer to directions for circular motion. The tangential direction represents the direction of the velocity vector at any moment for the object moving in a circle, whereas the centripetal, language centripetal, would be a word we'd use to describe the resulting force or acceleration. Okay, in the next video, I'll try to convince you more that the acceleration really is directed centripetally and not centrifugally. Thanks for watching.